Hello, this is the GonkBots CubeSat design review. We've been working on this project together as a group. The outline for the design review is first the smart requirements and the concept of operations, software architecture, mechanical layout, link budget, power budget, mass budget and bill of materials, data budget, and integration and test plan. For the smart requirements, our goal is to identify colored pieces of plastic in the ocean from a bird's eye view. In the first week, we'll create functions for plastic location, test ACDS code, and ensure data accuracy. Then in week 2, we'll finalize decision on ground station laptop. We'll test Pi Bluetooth and data transfer, and we'll ensure data transfer rates are consistent throughout deployment. Then in week 3, which is testing, we'll run through full deployment of procedures and test other CubeSat in different environments, along with tweaking our code and design. And in week 4, we'll finalize everything.
So for concept of operations, our first step is to initiate. This means we will power on the CubeSat and use Bluetooth and subsystems to start data collection through the Raspberry Pi. Our second step is to pre-launch it. So prior to launching the CubeSat, we will send subsystem data to the ground station through Bluetooth, and this will export current acceleration and angular rate. And using this data, in case of maybe something goes wrong, we have a failsafe where if the acceleration and angular rate is out of a specified range, it'll shut down the program automatically because of the faulty data. And then our third step is deployment, where it will continue data transferring and start image processing at specified data points. And if the image processing cannot detect, if the algorithm cannot detect an image to target, it will automatically shut down due to faulty image storage. And then our fourth step is data collection, where it will store data in a specified file through Bluetooth. And this will filter the data based on accuracy. So the most accurate will be in the top. And then the closeout phase is our fifth step, which we will check for data in a file and stop data transferring, shut down the image processing and kill flight software. And then the data should be already stored in the file, which means that it is all done.
Next, about software architecture, the requirements for our software is to identify colored plastics in the ocean, as well as take pictures from the Raspberry Pi camera. From a high-level design, we will take the image from the Raspberry Pi camera and then input it into a plastic locator algorithm. Through this, it will process the image and find all locations in the image where colored plastics are located. Then it will store the processed file. Below are some sample tests from the plastic locator algorithm. Some plans for software development is to integrate the plastic locator with the ADCS and flight software code. Here is the locate plastic code from the plastic locator software. It converts an image to an array of RGB values for each pixel. And then based on the pixel values in the image, it will convert the RGB values to HSV, which will identify if each pixel value is water, if it's blue, or if it's a colored plastic, if it's not blue. Through this, we can identify colored plastics.
All right, next up is going to be the mechanical layout. So for a basic CubeSat plan, the components are located here, right, in this CAD file. Here we can see basic things like the Raspberry Pi camera, the IMU, the solar panel, and the battery. So this is just obviously a basic CubeSat plan where it'll be surrounded by acrylic pieces fixed in with corner rails and hardware that interacts with the Pi. And we really wanted to make a simple and elegant design, which prioritized ease of access to finding every piece of hardware, and we can risk manage and make sure we have all the hardware. And if anything's wrong with the hardware, we can easily access it and make sure nothing's wrong with it. And we also prioritize having a lasting battery life, so our CubeSat can continue to do the image processing and flight software without having to recharge all the time.
Okay, so for our link budget, we made some predictions on how the signal between the Raspberry Pi and our school Wi-Fi, which is what we will be testing during our demo. So listed here are some of the calculations that we made. So we include the gain, transit power, and noise temperature of both the ground antenna, which is the school Wi-Fi, and the satellite antenna, which is on the Raspberry Pi. And through this, we were able to calculate various numbers such as the free space path loss, the EIRP, noise power, and the signal to noise ratio. And this helps us to determine how much data will be lost as the data travels through Wi-Fi signals. And the satellite moves through the orbit. Since we are testing in a relatively small space, the strength of link will vary a little and will fluctuate based on position depending on distance to the Wi-Fi router. And this is because the radius is used in the calculation of free space path loss. So as the radius increases, it's more likely that more data will be lost and that the link will be weaker. And since the orbit is circular, the link will fluctuate a little, but it will end up at the same strength at every revolution. And our estimates for the data speed is approximately 90 megabits per second.
All right, so for our power budget, we basically have two power components, the Raspberry Pi and then the camera IMU system. So for the Raspberry Pi, using the voltmeter, we found out that it, while it was idle, it took 2.29 watts of power. And then for the camera and IMU system alone took 0.195 watts. And based on the power producers that we were provided, our solar panel was faulty and it only gave us 2.3 volts with a current of 0.6 microamps, and which generated very low power, which it was not able to provide power for the Pi and let alone the camera IMU system. But the solar panel that we should have gotten, which would have been which would have generated 6 volts of electricity, it would have easily been able to power the camera and IMU systems. But for now, our main power producer is the fully charged battery, which the 10,000 milliamperes an hour, which gives us sufficient battery power to provide to keep our Raspberry Pi running for a long amount of time. And based on observations, it only went down by 1% after estimated 6 to 7 minutes.
We listed and calculated our estimated total mass for our CubeSat. The largest contributors to the total mass were the battery, which is 146 grams, the acrylic panels, which were about half, and the Raspberry Pi and power supply, which combined were about 46 grams. In total, the mass of our CubeSat is 413 grams, which is well below the max of an AIAA CubeSat, which is 1.3 kilograms.
When it comes to our data budget, we have a few different ways that we spend it. So the first way, and the data transfer that occurs in our CubeSat is transferred, well, the IMU acceleration data and the velocity are part of it, but also the image files, we put it into the Pi storage with Bluetooth. And so this process of picture capture and storing them, and then also analyzing them will take 3 to 4 seconds per image. And then also our data transfer itself will only take about 5 milliseconds, and out of range or faulty data would be filtered out in this process. And then secondly, we have the influence on the connectivity of operations, and this allows for fast and accurate data collection, but it also allows for fail-safe functions to help stop other faulty data that might have gone through.
For our testing, we'll have 5 different images with colored plastics in the waters that we'll test with the program. While testing, we will record the data and determine the accuracy and efficiency of our program. With this data, our team will get together and discuss and work to brainstorm new ideas to improve our new program. We'll be focusing on improving the program to be able to detect blue and clear plastic, increasing the scope of plastic detection, and identifying that non-plastic objects in the water are not actually plastic.
So for our summary, we really wanted to have a simple design for our CubeSat that could accomplish complex tasks, which is why we went with a simple mechanical design that had a lot of room for trial and error. This can include different orientations of the hardware or the camera or the Pi that either help us better identify the plastics. And we really wanted to test a lot of code to see what the best plastic locator would be. So while we have a very well functioning plastic locator function right now, we can always improve it. And we really do hope that you did learn about how the GonkBots team is hoping to identify plastic waste in the ocean. And we presented many ways to overcome this global issue that we see today. Thank you.